For a long time, the story of semiconductors has been a single contest. How thin can you go? But looking at IBM's latest announcement, the way I read it, the very ground of that contest might be starting to shift, away from how thin you can make things on a flat plane, and toward how you stack them in 3 dimensions. More than the headline numbers, sub 1 nanometer, 0.7 nanometer, I'd argue it's the thinking about how you stack that's going to matter from here. That's the kind of announcement this was.
Welcome to Semiconductor News Decoded. I'm Ty, with 31 years inside the semiconductor industry, bringing you the real view from the factory floor. Today we're looking at Nanostack, IBM's sub 1 nanometer technology, which they're billing as a world first. By the end of this video, you'll have a clear picture of what that headline 0.7 nanometer number really means, why the structure behind it matters more than the number itself, and where the shrinking of semiconductors is heading from here.
Here's today's news in one picture. Imagine a popular shopping street, and we'll lean on this shopping street image all the way through the opening section. There's a long shopping street on prime land right in front of the station. Plenty of people want to open a store there, but the length of the street is fixed. How many shops can you pack into that limited space? That has been the theme all along. Up to now, the way to fit in more shops has been to keep narrowing the frontage of each one, the width of the store. Halve the width, and you can line up twice as many shops on the same street. Everyone has been increasing the number of shops through this race to narrow the frontage. But now we've hit a wall. Narrow the frontage any further, and customers can't get in, and there's nowhere to put the goods. Physically, we've arrived at the point where you simply can't make it any narrower. And if you force them in any way, the walls of neighboring shops end up too close together, and they start interfering with one another. Voices carry straight through, the layout is cramped, and in the end, none of the shops can really operate properly. Simply making things narrower and lining them up side by side just doesn't work anymore. So the idea that emerged was to stack upward. In other words, to build upward, like a building. Add a second floor, a third floor, not just the ground floor, and you can fit far more shops on the same plot of land. And what's interesting about IBM's approach is this. They don't just stack each floor squarely on top of the one below. They offset them, shifting each one slightly. By offsetting, every floor becomes independent and can be built in the way that suits it best. More shops on the same land, and each one in its optimal shape. This is the heart of the picture. From here, let me walk you through what this actually looks like in the real semiconductor industry.
So let's get into the substance of the news. The star of today's story is IBM. These days, they're not a company that mass produces chips in their own fabs, but in fundamental research, they've kept running at the world's leading edge. They're something like a wellspring of the technology. In fact, one structure that is mainstream today traces its origins, when you follow the thread back, to IBM.
On June 25, 2026, IBM announced a sub 1 nanometer, 0.7 nanometer generation semiconductor technology that they're billing as a world first. The 0.7 nanometer generation is also called the 7-nm generation. The name of the new structure is Nanostack. By stacking transistors vertically, it aims to push past the limits of the flat, planar shrinking we've relied on until now. The scale of it is remarkable. According to IBM, a chip about the size of a fingernail could potentially integrate around 100 billion transistors. That's roughly twice the density compared with IBM's 2 nanometer technology. They explain that performance improves by up to 50%, or alternatively, power efficiency improves by up to 70%.
That said, this won't become a product right away. Applying it to mass production is, at the earliest, a possibility within the next 5 years. That's the stage we're at. This isn't about the phone in your pocket tomorrow. I think the accurate way to take it is as a signpost pointing toward the post-2 nanometer generation. In other words, the generation after next. Now, here's the part I most want to talk about. In the news coverage, that 0.7 nanometer number is getting all the attention. But what I really paid attention to is not that number at all.
The real core is Nanostack itself, the new transistor structure IBM has proposed this time. 0.7 nanometers is, in the end, just a signpost showing the result. What actually decides the contest is the way it's built behind that sign.
Let me set up a little background here. In today's leading-edge logic chips, a structure IBM invented, Nanosheet, GAA, gate-all-around, has become the mainstream. Samsung was first in the world to mass produce it at 3 nanometers, and TSMC's N2 and Intel's 18A have also entered mass production from the end of 2025. And IBM has now proposed Nanostack as the generation beyond even that. Nanostack is a new 3D transistor structure that belongs to the CFET, complementary FET family, that the industry is actively researching right now. But it isn't simply a matter of stacking up and down. IBM's single biggest distinguishing feature is that they arrange the stacked transistors in an alternating pattern, offsetting them slightly from one another. Why offset them? Because doing so lets you optimize each transistor individually, while at the same time packing them in at higher density. In terms of that shopping street from earlier, it's the idea of offsetting each floor, so every shop is in its optimal shape, while still increasing the count. Not make it even thinner, but stack it in 3 dimensions, and then offset the arrangement. I think there's a genuine shift in thinking right here. In recent years, the performance gains from shrinking have been approaching their physical limits. That is exactly why the industry as a whole is starting to move in the 3-dimensional direction. CFET, monolithic 3D integration, 3D transistors. This time, IBM has shown one of the leading candidates not as theory on paper, but in actual silicon. I see real significance in that.
Now, the impact on Japan. As semiconductors head from flat to 3-dimensional, the weight of processes like stacking, etching away, and binding together increases all at once. This could be a tailwind for Japan's equipment and materials makers, who are strong in deposition, etching, and binding. On top of that, IBM is a company that licenses out its research results instead of mass-producing in-house. And in fact, at that 2-nanometer generation, they partnered with Japan's Rapidus. This 0.7 nanometer work won't necessarily be handed over as is, but the point that Japan sits at the end of IBM's leading-edge research pipeline is not something to overlook.
If I put my read on it in one line, the competition in semiconductors has reached a turning point where the ground itself is shifting. From how thin can you go on a flat plane to how do you stack and arrange in 3 dimensions. The 0.7 nanometer number, the way I feel it, is no more than a signpost marking the entrance to that.
Let me wrap up. IBM has announced Nanostack, a new sub-1 nanometer, 0.7 nanometer generation technology. What deserves attention is less the number and more the structural idea, stacking transistors in an alternating offset pattern. As shrinking nears its limits, the axis of competition is shifting from thinness on a flat plane to the way you stack in 3 dimensions. Mass production is still some way off, but I think this is a big move that points toward the next direction for semiconductors.
That's all for today. I'll keep bringing you semiconductor news and analysis, so if you found this useful, please like, subscribe, and I'll see you in the next video. This has been Ty on Semiconductor News Decoded.